So what we're looking at in this unit is supplemental to what we have just talked about with the tests of significance. Okay? Really, we could have made it like one big chapter, but it's important to kind of lay the groundwork, understand those steps, okay? Creating hypotheses, getting the test statistic, get the p-value, what are your conclusions, and now we can kind of like backfill and look at different bits and pieces and expand on some of the ideas that we talked about in that process. Okay, so we have two main goals, two main targets here. We're going to concentrate on this first one today and probably get to this second one on Tuesday in our next class. Meet the necessary conditions for using both confidence intervals and these tests of significance. Okay, we need to understand that we're playing by the rules, that we're allowed to use these equations to get the proper interpretations. And sometimes it's easy to get into a habit where, all right, here are the numbers, put them into the equations, spits out an answer, there's the answer, it's what it is, it's the truth. But just as important in statistics is justification that you're allowed to use the equations. If you get numbers that aren't accurate, that aren't actually what's happening in the population, the whole purpose was meaningless, the whole process that you did. And so just as important as the calculations themselves are making sure that we have met the conditions to use these tests. And then, as I said, Monday we'll look more closely at error. So what we've talked about with a confidence interval and our test of significance, these are called Z procedures because they're based off of the normal distribution and Z-scores. Now that we've learned this like 4-step process, that process is going to hold true for a number of different tests. Okay? The rest of, I'm not going to say exactly the rest of the year, but the next several weeks as we go into our next unit is going to be learning new test after new test after new test that still follows these same procedures. We just have a different model, so it's a slightly different equation, but our interpretations are the same thing. We'll still get a p-value. We still have hypotheses that we need to determine which one is correct and supported by our evidence. Okay? So remember, a confidence interval, you have our sample value, or sample mean in this case, and then we're going plus or minus a margin of error that's dictated by the sampling distribution. Okay, that's what we have this standard error measure in our Z star is how many steps do we want to be above and below based off of our level of confidence. And here is that modified Z-score equation for our Z test. Now, when we're working with these procedures for inference, okay, whether that's a confidence interval or a test of significance, okay, these can only be trusted under specific conditions. And where that data comes from, it matters. If you're not working from accurate data that's well representing the population that you have in interest, then the numbers that you get, the boundaries for your confidence interval, the p-value that you get, it's worthless. Okay, so everything that we've done in the first semester builds up to this. You can't expect to get a good result based off of poor data. If your data does not come from a random sample or randomized comparative experiment, your conclusions, it says may be challenged, they will be challenged. Okay, if you're publishing something, we've done a little bit of this our first semester, and we're reading over studies that we question how they were performed, how they were set up, and how they were executed. Okay, and we kind of criticize them for that. The expectation is that you have a good methodology to enable you to get meaningful results and meaningful conclusions. Practical problems such as non-response or dropouts from an experiment, they can hinder the inference. Why are people not participating or not wanting to participate? That is something that it's one of the most challenging things for pollsters and people collecting good data to overcome in this day and age. Different methods are needed for different designs. So as I said, we have only learned the procedures for a single test so far. Okay, a z-test for a single population mean. But we'll be looking at proportions, difference of two means, difference of two proportions, different types of tests, t-test, chi-square test, test of ANOVA. The conditions lend themselves to a type of test. So it's up to you to look at your data and kind of preemptively determine what test would be appropriate. There is no cure for fundamental flaws like voluntary response. There's this idea that sometimes, especially with the confidence interval, that we've got some wiggle room. There's a quote about statistics that says, being a statistician means never having to say you're certain, right? Like, this is what it is, but there's a margin of error that means it could be below or above. I'm saying it's somewhere between here. Okay? So sometimes people approach statistics and that precision isn't important. Well, that doesn't mean that you can willingly have flaws in your execution. There is no cure for fundamental flaws, like a voluntary response sample. We talked about this, how if you have people who are going out of their way to participate and provide data, provide their opinions, those people are probably strongly opinionated on that issue, and you're going to get biased data, biased results. So yeah, you can go through the process with those numbers and you'll get some confidence interval, you'll get some p-value, but it's not going to represent a larger population beyond those biased volunteers. Okay? There's no way that you can modify the numbers or modify the calculations to adapt for something like that. Now, we had said, and actually I want to go back a couple slides real fast here. To use these procedures, we had said that there were three things that we needed to keep in mind. Okay? That the data is obtained from a simple random sample, that the population has a normal distribution. Remember, normal distributions, we see them from time to time, often natural measurements occurring across a homogeneous population. Okay, so like adult males have a normally distributed height. Okay? You wouldn't want to mix them with adult females. Okay? You no longer have a homogeneous population. Same thing, you wouldn't want to have a very broad age range. Okay? But that population distribution isn't all that common. We wouldn't be spending the time if we really needed that population distribution to be normal. We wouldn't be spending as much time as we are with this. So we'll talk about that in a minute. Lastly, this is the one I've been making fun of for weeks now, that we know the population standard deviation sigma. Okay? It's absurd to think that we're doing all this work to find the population mean, but we happen to know the population standard deviation when this measure is based off of the mean. You can't get this without knowing the population mean. So we'll work our way through that here. But those three things are not practical assumptions. Okay? So we're going to talk about how we work through that. What is the shape of the population distribution? Okay? Well, many of the basic methods of inference are designed for normal populations. But fortunately, this condition is less essential than where the data come from. Okay? We said that in our sampling distributions from the central limit theorem, you don't really need a normal distribution for the population as long as that sample size is big enough. Because these Z procedures are based off of the sampling distribution will be normal. So we can still use these calculations as long as that sample as long as that sample size is large enough. Any inference procedure based on sample statistics, like the sample mean, okay, that's what we've been using, X bar, that are not resistant to outliers can be strongly influenced by a few extreme observations. So we know that mean is susceptible to outliers. And in the first semester when we were talking about that, we said, well, if you have some extreme values, maybe a better measure of center would be median. But it's been a long time since we talked about median. And in reality, we're probably not going to talk about it that much the rest of the year. There are some statistical tests that use median, but they're not really usually taught in like entry-level statistics courses. Okay? But there are tests out there that use it. So down the road, if you're in graduate school and you're performing some big research project and you have extreme values, maybe mean isn't your best option because it's susceptible to those extreme values. Okay? A confidence interval that really probably should go from here to here, but because you have extreme values, it's pulling that entire interval in the direction of those extreme values. That's what happens. Okay? When the foundation of your analysis is based off of some statistics that are susceptible to these extreme values, you need to think about how that impacts your results. You might be getting a bunch of results that are systematically always below your confidence interval because of that extreme outlier. Here's an example problem. It says, a survey of licensed drivers inquired about running red lights. And one question asked, of every 10 motorists who run a red light, about how many do you think will be caught? Okay, this is a survey question to people in this town. Out of 10 people who run a red light, how many do you think are caught? They had 880 people respond to this question, and the mean answer was 1.92 out of 10. Standard deviation for this sample was 1.83. Now, because it's a pretty large sample, 880, that sample standard deviation is going to be close to the population standard deviation. So we're just going to use that same number, 1.83, for our calculation. So letter A says give a 95% confidence interval for the mean opinion in the population of all licensed drivers. So I did this in GeoGebra. Okay? We have our sample mean value of 1.92 right at the center of our confidence interval, and we're going plus or minus 2 of these standard errors, which works out to be a value of about 0.1209. So that's going to give us a confidence interval. In this case, we are 95% sure that the average number of people who are caught running red lights out of 10 is between 1.8 and about 2.0. Get a pretty narrow margin here, which is good. It's based off of a substantial sample size. So we're 95% confident that our true average of the population is between these two numbers. Now let's think back for a second here. Letter B says the distribution of responses is skewed to the right rather than normal. This will not strongly affect the Z confidence interval for this sample. Why not? Well, let's talk about this first part here. The distribution for the population is not normal. Instead, it's skewed right. So something like this. Here's our frequency distribution. It could be 0 through 10. Maybe some of you think that 0 of these 10 people are going to get caught running a red light. Others might think that all 10 of them are going to get caught. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But think about why this cannot be normal. A normal distribution, you have the bulk of the data right at the mean and then symmetrically balanced in both directions. Our mean here is 1.92, and so a little shy of 2. There's not much room to go in the left direction. Okay? You can't go negative. You can only go to 0. So you're probably going to have a very abrupt ending over here, but then some extreme values going off to the right. There's probably a few people who think, yeah, they're going to catch 8 out of 10, 9 out of 10, all 10 of these people running red lights. So it's pulling that mean in this direction. It's skewed to the right. So this is clearly not a normal distribution, but that's okay. Again, central limit theorem says, in theory, if we're to take a bunch of these samples of 880 people, we're going to have a normal distribution of those samples, and that is what this confidence interval and these Z procedures are based off of, the sampling distribution, not the population's distribution. Questions on that? All right, now letter C. The 880 respondents that we've used for our sample size. They are a simple random sample from completed calls among almost 46,000 calls to randomly chosen residential telephone numbers listed in telephone directories. Only about 5,000 of those calls were completed. This information gives 2 reasons to suspect that the sample may not represent all licensed drivers. What are these reasons? Look at this. What are some flaws with this, or things that make us very suspicious? We know this mean was calculated across 880 people, but they tried contacting 46,000 people. Of those 46,000 attempts, they were able to complete 5,000 calls, or get through to 5,000 of those people, but only less than 20% of them, 880 of those completed calls, actually completed this survey. That's the biggest thing that stands out, is that we have a very high non-response rate. Okay? Non-response is a big problem because it starts to make you question, why are these people refusing to participate? And those who do participate, it's almost turning them into a voluntary response. Do they have some unifying characteristic that makes them more likely to respond? And do they have similar beliefs or opinions that are making your results more biased? Possibly. Maybe not with questions about running red lights, but certainly with political opinions and things like that. 2 of the biggest problems in political polls right now, we've seen it in the last 2 presidential elections as to why the polls are not matching what happens on election day, is because of high non-response rates and undercoverage, not reaching parts of the population. And that's our second flaw right here, undercoverage. They obtained this sample based off of telephone numbers, residential telephone numbers listed in telephone directories. Telephone directories are made up of old school landlines. Who's more likely to have a landline? older people. So you're pulling from a list, a sampling frame that skews towards older people. Okay? Younger opinions, again, I don't know if that has any impact on if you feel people are running red lights and getting caught, but it could bias your results. Okay, so those are the two big flaws. You're not reaching a segment of the population. It's undercovering that population that you're trying to represent based off of this telephone directory that skews towards a particular age group. Questions about that? All right, sticking with confidence intervals. A sampling distribution shows how a statistic varies in repeated random sampling. Okay? That's what a confidence interval does. Okay? If we were theoretically to do random sample after random sample of this same size, that makes up our sampling distribution. Now this variation causes random sampling error because the statistic misses the true parameter by a random amount. That's okay. There's this natural variation that's always there. We flip a coin 10 times, we expect 5 heads, 5 tails. If we get 6 and 4, it's all good. So the confidence interval is meant and built to account for that. The margin of error in a confidence interval, it ignores everything except that sample-to-sample variation due to choosing the sample randomly. So I had said that sometimes we get this misconception that it's okay to be imprecise, or it's okay to maybe have a little bit of a flaw in our methodology or whatever, because that confidence interval says, well, I don't need it to be right there. I'm 95% confident that it's between here and here. So there's my safety net. That's not what it's meant for. The confidence interval is not a catch-all to help you correct any mistakes or flaws along the way. It's just there to account for the natural variation. That this is what we got in our sample. It may not be exactly what's happening in our population, but we're pretty sure the population is between here and here. Okay? The margin of error in a confidence interval covers only random sampling errors. Practical difficulties such as, there it is again, undercoverage and non-response. They're often more serious than random sampling error. Goes through that idea that if you're pulling from bad data, you're going to get bad results. The margin of error does not take into account such difficulties. So you need to be aware of that, that it's not the safety net to help you overcome any flaws with your methodology. It's purely there for the random sampling variation. Questions on that? Here's another example. It says a July 2013 Gallup poll asked how often, if ever, do you eat at fast food restaurants, including drive-through, takeout, sitting down in the restaurant. Of those sampled, 47% indicated that they do so at least weekly. Gallup announced the poll's margin of error for 95% confidence as plus or minus 3 percentage points. Which of the following sources of error are included in this margin of error? All right, well, we just talked about this. It's talking about how Gallup went about creating this confidence interval. So 47% at the middle, minus 3, you're going down to 44%, up to 50%. We're 95% confident that between 44 and 50% of Americans eat at a fast food restaurant at least once a week, is what this is saying. Now, the way Gallup obtained this data, they dialed landline telephone numbers at random. There's that landline again. So it missed all of the people without landline phones. Okay, so we're skewing older, including people whose only phone is a cell phone. Okay? This poor methodology, this poor use of a sampling frame, that is not covered by the margin of error. Okay? Margin of error does not account for that. Secondly, some people whose numbers were chosen never answered the phone in several calls, or answered but refused to participate in the poll. Non-response, not covered by the confidence interval. Letter C, there is chance variation in the random selection of telephone numbers. That is what the confidence interval is made for. Okay? So that maybe if you were to actually perform an accurate census and interviewed everybody and they answered honestly, maybe you get 48% answering that way. Okay? There's natural variation here. Our sample had 47, we got 48. It's in our margin of error, it's in our confidence interval. The world is good. Okay? That's the only thing that the confidence interval does. Now, shifting gears a little bit from the confidence intervals to the significance tests. I had said the other day that the significance tests essentially answer a yes or no question for you. Yes, the evidence that we have collected is significant enough or convincing enough to reject that null hypothesis and make us accept our alternative. Or, no, it's not convincing enough. What we had previously held as true is still true. It's a yes or no question. Is it bigger than 0.05 or is it smaller than 0.05? Now, sometimes, because it's so clean cut, society has kind of developed an over-reliance on p-values and on statistical tests. There are still problems with that, and people kind of expanding on what they can believe based on that. Now, significance tests are widely used in most areas of statistical work. Some points to keep in mind when you use or interpret significance tests are how small of a p-value is convincing. Now, we said a lot of times we're using this alpha level of 0.05. If p is low, you reject the O. Reject the null hypothesis. But what if you come back with a p-value of 0.047? Yeah. Yep, I've done my research. I'm so glad that my p-value is just under 0.05. It's statistically significant. Reject the null, accept the alternative, and I can buy into my results. I have legitimate results in my population. Oh, you just barely got under that threshold. Right? And we had said that a lot of tests, medical tests, things like that, they have a lower a higher threshold and a lower alpha level than 0.01 or 0.001. So you're kind of setting your own bar. It's like if we allowed you to set your own grade scale and say, well, anything above 70% is an A. So you're coming in with like 71% and it's like, look, I'm a straight A student. Same kind of thing. If you're setting your bar, well, I came back with a p-value of 0.08. Let's just make the alpha level 0.10. Yay, it's significant. Okay. How small is convincing? As opposed to if you come back with a p-value of 0.00001. Remember, p-value is a probability. So it's not just some like artificial number. This is representing that there is almost a 0% chance that this null hypothesis is true and that you would get this or expect this and get this just as natural variation alone. That's incredibly rare. So there's probably more to it. There's something going on. Reject that null hypothesis, accept the alternative, as opposed to, almost 5% of the time we're going to get this as natural variation, but the rules say it's under 0.05, reject the null, accept the alternative. Okay. Again, how small of a p-value is convincing? It says here, the purpose of a test of significance is to describe the degree of evidence provided by the sample against the null hypothesis. How small a p-value is convincing evidence against the null hypothesis depends mainly on two circumstances. If that null hypothesis represents an assumption that has been believed for years, strong evidence, which is a small p-value, will be needed. We know that us as human beings, we get stuck in our ways. Something might be obviously false, but it's long believed to be true, so we still believe it. Okay? Old wives' tales, like things like that. Like we still do that. Contrary to all evidence. So when there's actually like something that has some scientific basis, and you're going to come along with your test and my p-value, if you're trying to throw out something that's well ingrained in society's belief, you better have a very convincing p-value to go with that. Not to mention accurate data that's big enough and well representative. Also, if rejecting that null hypothesis means making a costly changeover, and by costly we could mean, monetarily expensive, or costly in terms of time and effort, you're going to need strong evidence to back you up. And that strong evidence is a very small p-value. So think about this. Like, these procedures, I've said this since the first day of school. Statistics is a tool for helping you make decisions. Here is your tool. This is what's guiding you in your decision-making policies. So if you are in a position of power or making these decisions, you're running a company, you're running a government, this cost, it weighs heavily on your mind. You need convincing evidence to support that decision-making process. Now, we know that the significance depends on the alternative hypothesis. Okay? We've said this alternative could be one-sided or two-sided, and the two-sided is exactly double the one-sided p-value. And that's okay. Like, we expect that because it's a normal symmetric distribution. Okay? The data on both sides, we're not implying any direction for our difference. The evidence against the null hypothesis is stronger when the alternative is one-sided because it is based on data plus information about the direction of possible deviations from the null. If you lack this added information, always use a two-sided alternative hypothesis. The two-sided is the safe way to go into a study. Okay? We saw it in some of our examples the other day, that if you have no idea, like it was the blood pressure of the people, okay, there was this mean blood pressure for the population. You thought that your staff was different. You don't know if it's higher or lower, but you think it's different. You go into it with a two-sided alternative. Okay? You're testing both directions, and it's harder to reject the null hypothesis because once you go through and you get your amount of data in the curve, or in the tail of the curve, you're multiplying it by 2. So obviously, when you multiply by 2, it's harder to stay under that 0.05 threshold. You would only use a one-sided alternative hypothesis if it's ridiculous to believe that it could be in a different direction. Okay? So you're only looking at one direction of deviation. Or you may have some existing evidence. I had said this the other day in terms of our ethical procedures. You have some existing evidence of a trend going in one direction. So you're going to set your one-sided alternative hypothesis and then go out and collect brand new data, and it should be going in that direction. Okay? If it's not going in that direction, then you've got bigger problems than just setting up your hypotheses. Okay? You're getting data that then goes in the other direction. Yeah, you kind of need to go back to square one with that. Okay? But the safe way to enter a test is with a two-sided alternative hypothesis. We also saw how the sample size affects statistical significance. We were playing around, we were doing our p-hacking on Wednesday in GeoGebra and showing how changing the sample size but keeping the same sample mean or the same rate, that can change your level of significance. If you see a trend happening across a larger group of people, a larger sample, you are more certain that this is truly what's happening in the population. Okay? So it's easier to get statistical significance if you have a much larger sample size. You can look at the procedures, the equation itself. Okay, big sample size down there in the denominator of the standard error. You're dividing by a bigger number. Okay, so that step size is going to be smaller. It all works out. On the flip side of that coin, if you go into a study with admittedly a pretty small sample size, you might have legitimate results, or you're going in the right direction, but because it was not a big enough sample size, the difference that you observed was not strong enough evidence to say that we're certain that this is truly what's happening in the population as a whole. So sometimes legitimate trends might be thrown out because it's not observed across a large enough group of people. Okay? So this all boils down to this idea of statistical significance versus practical significance. They are not the same. Statistical significance is less than 0.05, yes, our data is statistically significant, or bigger than 0.05, fail to reject the null hypothesis, it's not a statistically significant difference. It's the answer to that yes or no question. But in terms of practical significance, just because something is under 0.05 doesn't necessarily mean that that difference is practical to you. Okay? I think I shared an example, a case study at the beginning of the year that was done throughout the 1980s, and it wrapped up in the late 80s, early 90s, about the relationship between older adult men taking aspirin daily and the likelihood of having a heart attack. And that study was a huge study. It was based off of a sample of over 22,000 adult males. And if you look at the data, the difference between the test group and the placebo group is just very small. Okay, the rate of heart attack for the placebo group is like, I'll have to pull it up and share it with you guys, but it's like 1.9. Okay, so 1.9 heart attacks per 10,000 individuals, I think, compared with like 0.7 heart attacks for the aspirin group per 10,000 individuals. So it's a slight difference. However, across a sample size of 22,000 people, that slight difference is significant. If it had been a smaller sample, you're not going to have a statistically significant result. But there is practical significance to that. Because if you look at those rates, it reduced the risk of a heart attack by more than half. Okay? So that slight change had practical significance. Okay? There are more sophisticated ways to measure this that you might look at if you take a more advanced statistics class down the road. Okay? You talk about the power of a test. Okay? You'll be doing further analysis with the p-values. But it helps you determine how strong that practical significance is. You want to be aware of multiple analyses. And that seems a little counterintuitive, right? Like, you get a doctor, I'm going to perform a battery of tests to figure out exactly what's going on. Okay? Well, the reasoning of a statistical significance, it works well if you decide what effect you are seeking, design a study that catered to measure that effect. And you search for it, and you use a test of significance to weigh the evidence that you get. But if you have a set of data that you've collected, and you're running like 25, 30 hypothesis tests, and it comes back and it's like, not significant, not significant, not significant, oh, this one's significant. This is what I'm going to publish my results about. Like, that's the old phrase, like you're throwing crap against the wall and see what sticks. Okay? Beware of when you see things like that. Because they're publishing the results that were meaningful to them. Okay? The things that came back that were not meaningful, swept it under the rug, or just didn't really bring it out to the forefront. Sometimes they'll mention them, but the headlines are about the things that they found as significant. Here's a passage from our textbook about that. It says, a sample survey shows that significantly fewer students are heavy drinkers at colleges that ban alcohol on campus. Now, significantly fewer is not enough information to decide whether there is an important difference. Again, talking about statistical significance versus practical significance. Not enough to determine if there's an important difference in drinking behavior at schools that ban alcohol. How important an effect is depends on the size of the effect as well as its statistical significance. If the number of heavy drinkers is only 1% less at colleges that ban alcohol than at other colleges, this is probably not an important effect, even if it is statistically significant. Okay? And it says in parentheses, ask yourself if you would describe 1% as significantly fewer when talking with a friend. In fact, the sample survey found that 38% of students at colleges that ban alcohol are heavy episodic drinkers, compared with 48% at other colleges. That difference is large enough to be important. There's a 10% difference there. However, this observational study doesn't prove that an alcohol ban directly reduces drinking. It may be that colleges that ban alcohol attract more students who don't want to drink heavily. Okay? So again, goes all the way back to what we talked about in our first semester with the methodology. Another example here. It says, might the radiation from cell phones be harmful to users? Many studies have found little or no connection between using cell phones and various illnesses. Here is part of a news account of one study. Okay, so this is an excerpt from a news story. A hospital study that compared brain cancer patients and a similar group without brain cancer found no statistically significant association between cell phone use and a group of brain cancers known as gliomas. Probably pronounced that wrong. But when 20 types of glioma were considered separately, an association was found between phone use and one rare form. Puzzlingly, however, this risk appeared to decrease rather than increase with greater mobile phone use. Now, our analysis says here, think for a moment. Suppose that 20 null hypotheses were saying that there's no relationship between cell phone use and brain cancer. For these 20 significance tests are all true. Pretend that the nulls are true in all 20. Then each test has a 5% chance of being significant at the 5% level. That is what an alpha level of 0.05 means. So that is telling you that statistically, we expect that one of these is going to happen due to natural variation alone. That we're going to get a p-value that is attributed to natural variation. Results this extreme occur 5% of the time just by chance when the null hypothesis is true. Because 5% is 1/20th, we expect about 1 out of 20 tests to give a significant result just by chance. That's what the study observed. And that's why you have to be careful when you throw a whole bunch of tests at the wall and see what sticks. If you get a significant result, okay, we know that these are imperfect tests, and by looking at only the one that stands out, it's not necessarily standing out because it's a legitimate association. It's probably standing out because that's what you expected by the rules of probability. So you have to be on the lookout for things like that. All right. This is our last slide, and then we'll get into error on Tuesday. So, when you're planning a study, I'm sorry, go ahead. When you're planning a study, and I know that like a lot of our work that we've done so far has just been academic and like going from the textbook, preparing for a test, that sort of thing. Okay? But we are working towards actually collecting our data and actually measuring and analyzing it ourselves. You want to plan a study with a particular test of significance in mind. A wise user of statistics never plans a sample or an experiment without also planning the inference. The number of observations is a critical part of planning the study. So you go into this thinking like, well, I'd like a margin of error of about 3% or less than 5% or something like that. You're not going into it thinking like, my sample size, I don't know, is 50 big enough? Is 100 big enough? No. We know that our margin of error, okay, that thing that we add on plus or minus to our sample mean, is calculated by z star times sigma over the square root of n. Here's our standard error. There's our z star value, typically 2 if we want a 95% level of confidence. That gives us the margin of error. So algebraically, we can tweak this equation to solve for the sample size that we need. If I want a margin of error of some set amount, solve this equation for n, or just rederive this, you can see n is equal to the z star times that standard deviation, divided by the margin of error, all of that squared gives you the appropriate sample size to get your desired result. Okay? So we'll be using this equation to help us determine what an appropriate sample size would be for our desired margin of error. Don't just be thinking like, that sounds big enough. And then you come back and you have a margin of error that's like huge. Okay? You're not going to get any legitimate results from that. Okay, anybody have any questions here? I know that's long-winded, but it's a big process. Okay? And as I said, we laid the groundwork by looking at the full process for the test. Now we're kind of like backfilling and kind of supplementing and determining like, well, this is good, we want to focus on this. If we want this, we need to do this or make sure we're watching out for this. And we'll practice, we'll look at more examples before we start to look at more tests. As I said, on Tuesday we'll talk about error. Okay? What if we do everything right? By the book. We reject the null when we're supposed to, fail to reject the null when we're supposed to. But we find out after the fact that we were wrong. What are the consequences of that? And if we know our consequences in advance, maybe that affects our decision making during the process alone. If we have some catastrophic consequences, if we were to reject, and that's really not what we should be doing, we better be pretty certain that we're doing the right thing. Okay? All right, so we'll stop here for today. Pick up on Tuesday. Hope everybody has a nice weekend. Okay? You guys at home, free to sign off.